is a misnomer. It's not chaos. It's not randomness that can't be understood. In fact, the whole point of it is to try and make sense out of nature, and a lot of progress has been made doing that. So that said, the idea behind what we call chaos scientifically is an attempt to try and find order in what had previously been a very difficult to understand physical situation, namely the science of nonlinear, classical nonlinear motion. We tend to think of motion as linear in the sense that if I make a very small change to how I start out, it ends up being a very small change whatever time later. So if I launch a particle from here, a projectile, and it launch it at a certain angle, at a certain speed, and it'll follow a trajectory like this. On the other hand, if I change the angle slightly, it follows a trajectory like this. Or if I launch it a little bit faster, it might go a little bit farther. These small changes here lead to small changes here. And that will always be the case. The change can grow as a function of time, but the percentage contribution, or the fraction by which the result changes at the end, is still very small. In fact, it's linear. If I make a fraction of a percent change here, that same fraction of a percent change is what happens later. But that's only in systems that are described by so-called linear differential equations. And even though that's what we spend most of our time studying, or students get most of their time being taught, an enormous number of physical situations are nonlinear. Many examples. The most common example, which we gloss over all the time in introductory physics, is the pendulum. The pendulum swings in a way that if the angle of swinging is not very large, we can approximate it by a linear differential equation, and that motion looks just like a so-called simple harmonic oscillator, and that's the way it's almost always taught. On the other hand, if that pendulum ever gets swinging angles that are very large, that becomes a nonlinear differential equation, and the motion is very different. In our class, we talked about what happens if I take this nonlinear pendulum and I start applying a kick to it periodically, the same way a child might try and move a swing by pumping. After a while, the motion of that pendulum gets to be such large angles that it can swing around and behave all sorts of strange ways. And that is a prototypical nonlinear situation. If I change the initial conditions by a little bit, then the motion of this pendulum becomes wildly chaotic. And trying to understand those behaviors is important, more than just an academic exercise. Historically, the route to nonlinear physics and chaos began with a fellow who was trying to understand how to predict the weather. And he discovered that you had to use a computer program to calculate or solve the equations that he came up with for the weather, but those equations would give you different answers if you started out only slightly differently. And he came to appreciate mathematically how difficult it is to predict the weather, because if you change the so-called initial conditions, you get wildly different results out. It's impossible to know very precisely what the temperature and air pressure are at every point on the Earth at one time. So you can never make a precise measurement of what the weather is. People have been working on that for a while.